Jai Hind, welcome to class of Analog and Digital Communication. And we are going to talk about the digital modulation scheme QPSK today. First of all, we go with the definitions. What do we mean by digital modulation and what do we mean by QPSK? Digital modulation is a kind of scheme where your binary bits, messages in the form of binary bits, and that do modulate a very high frequency carrier wave. Here, the basic forms of digital modulation schemes that we have studied so far is ASK, FSK, and PSK, and QPSK is a variant of PSK. In ASK, the amplitude of the high frequency carrier wave is varied with respect to the input binary bits, and in FSK, the frequency of the high frequency carrier wave is varied, and in PSK, phase of the carrier wave is varied with respect to the input binary bits. Right. PSK has various different variants. Like in previous lecture, we have studied about BPSK, binary phase shift keying, which is the simplest form of PSK. Right. In PSK, we have studied that it uses one bit at a time. That is, the symbol is composed of one bit only. That is, single bit is responsible for varying the phase of the wave, or at the receiver side, by reading the phase variations of the modulated waveform, what we can predict is just one bit at a time, right? Whereas in QPSK, we use die bits. That is, my symbol is represented by 2 bits at a time. That makes number of possible combinations or levels equals to 4. As we know that m equals to 2 to the power n. So in QPSK kind of scheme, we use die bit. So with the help of die bit, we do make changes in the phase of the carrier wave. That is, my die bit is responsible for phase variation, right? So here, the possible number of combinations that I can obtain with the help of die bit is 0, 0, 0, 1, 1, 0, and 1, 1. These are the possible combinations that I can make with the help of 2 bits, right? So, corresponding to these die bits, there will be phase variations, right? So, we are going to study all of this in detail. And so, QPSK is a variation of BPSK and is also called as double sideband suppressed carrier modulation scheme, which sends 2 bits of digital information at a time, called as, we may call it bits or die bits as well. Instead of the conversion of digital bits into a series of digital stream, it converts them into bit pairs. True. This decreases the data bit rate to half, which allows space for the other users. So in a way, if I compare BPSK with my QPSK, with single phase variation, in BPSK, single bit is transmitted. Whereas with single phase variation, in case of QPSK, my die bits are transmitted. So I can say that QPSK is bandwidth efficient, that in the equal bandwidth, it transmits double the amount of data as that of BPSK. That's why we prefer QPSK over BPSK. Now let's talk about QPSK modulator, how to generate such kind of waveform, what kind of modulators do we use. So we'll get back to the slides. Let's see how QPSK modulator looks like. My QPSK modulator looks like this. We need 2 product modulators. As we know, for generation of BPSK, we just need 1 product modulator, but for generation of QPSK, we will need 2 product modulators. So these 2 product modulators are used in 2 channels, where the upper channel can be called as I channel and the lower channel could be called as Q channel. And we are not going to send die bits to each of the channel. We are going to split the die bit at every instant, at every symbol duration, and we are going to pass the even bit to the I channel and odd bit to the Q channel, right? And what happens later? Another input to the product modulator should be the input binary bit. One input is input binary bit, right? The message signal, which is binary in form. Another input should be the carrier. Carrier is generated locally here, so I'm using the term local oscillator here. To my in-phase channel, my carrier is the original form of carrier, and to the Q phase channel, my carrier is provided with a phase shift, 90-degree phase shift. So let's suppose if I am passing here cos wave, I'll be passing sine wave here, right? So in the beginning, I'm using a bit splitter, right? That will be converting serial, my bits from serial to parallel. Even bit goes to I channel, odd bit goes to Q channel. And as I know that this kind of product modulator will be generating my binary phase shift key, so I can assume that two BPSK signals are generated at I channel and Q channel, and finally these two are combined here and we get the output, right? Let's see. The QPSK modulator uses a bit splitter. True, I've shown you that. Two multipliers, or I can call it a product modulator, with the help, and also a local oscillator. To a product modulator, there will be two input. One of the input is my binary message bit, another input is given through carrier, right, which we generate with the help of the local oscillator. A 2-bit serial to parallel converter, it is required after bit splitting. I need to send my serial bits into parallel manner, and a summer circuit. Summer circuit is needed at the end to combine my two BPSK to form a QPSK. Right, following is the block diagram. I've shown you the block diagram. At the modulator's input, the message signals even bit, that is second bit and fourth bit and sixth bit, 8th bit, correspondingly 10th, 12th, so on. This will go to the I channel, in phase channel, whereas odd bits like my first, third, fifth, and so on, these are separated by the bit splitter and are multiplied with the same carrier to generate odd BPSK, right, called as PSK, and even BPSK called as PSKQ, right. The PSK signal is anyhow phase shifted by 90-degree, right, as to the second product modulator, that is the product modulator of the Q channel, in providing carrier with 90-degree phase reversal before being modulated. True. The QPSK waveform for the 2 bits input is as follows, which shows the modulated result. So after the modulator block diagram, I am going to show you the waveform, how it looks like, right? So I hope this is clear. Input message, binary bits, 2 bits at a time. First two, next two, and bit splitted, gone to the product modulator. Another input is carrier to this inverted carrier, 2 BPSK generated, summed, and we get QPSK, right? This is how my waveform must look like. If this is my carrier, phase shift must be observed, right? If for die bit 0, 0, if there is some phase shift, for 1, 0, there should be some phase shift, for 0, 1, there should be some phase shift, and for 1, 1, there should be some phase shift likewise, right? Right? You can observe here 45-degree phase shift. These phase shift will be clear when I show you exactly how QPSK waveform we do generate. that I'm going to show you after we cover this modulator and demodulator. And now the question is, at receiver, how do we demodulate QPSK? The QPSK demodulator again will use two product demodulator circuits with local oscillator, two bandpass filters, two integrator circuits, and two parallel to serial converter. Let's see. This will be my modulated waveform, right? Again, at receiver, we do need two product modulators. See, one product modulator is here, another product modulator is here. To one of the input, I am providing the, to both the product modulators, we are providing the modulated waveform. Whereas another input that we provide is locally generated carrier wave. To this, I am passing the carrier wave as it is, whereas to Q channel, I am passing the carrier with 90-degree phase shift, right? So this is a kind of coherent detector, right? Then I do use bandpass filters, then integrator. Same here for Q channel, bandpass filter and integrator. And finally, the result that we obtain in the form of bits that are again converted from parallel to serial to obtain my data, right? So this is how my QPSK demodulator looks like. We use two product modulators, local oscillator, two bandpass filters, two integrator, and a 2-bit parallel to serial converter. True. The two product detectors at the input of demodulators simultaneously demodulate the 2 BPSK. 2 BPSK are simultaneously demodulated, and each demodulator will give 1 bit at a time, and these are again converted from parallel to serial form with the help of this 2-bit parallel to serial converter. The pair of bits are recovered here from the original data. These signals after processing are passed to the parallel to serial converter, right? So far we have covered the basic definition of QPSK, its advantage over QPSK, how it can be generated and demodulated, right? Now let's check upon how does my QPSK waveform actually looks like. That could be made clear with the help of this waveform and with the help of this truth table. If I talk about the truth table of QPSK, or what kind of phase variations I do obtain in QPSK. So as discussed before, in QPSK, dibits are responsible for a particular phase, right? So what do we obtain here is 4 levels of phase shifts, 4 kinds of phase shifts, each phase shift corresponding to dibit, right? And these are my possible dibits. Let's suppose if I talk about the modulator, what do I give input to my I channel and what do I give input to my Q channel? Non-inverted, 1, inverted, right? So if I consider my quadrant is of 360-degree, I have to divide it into 4 parts, right? My each quadrant must be separated from the other with 90-degree, right? So if I consider, we can see here from 45 to 135 there is a phase shift of 90-degree and there is 1 bit variation. 1 remains same, there is 1 bit variation. For one bit variation, there is a phase shift of 90 degree. For another bit variation, again there is a phase shift of 90 degree. For another bit variation, I can observe there is a phase shift of 90 degree. Right? I can easily say that if I consider this as quadrant, here my die bits must appear. Right? How do these should appear? For 1 1, for 45 degree, it's 1 1. Right? For 135, that is 45 plus 90, it's 135, 0 1. Right? For 225, right, this is 0 0. And for 315, or which could also be called as minus 45, the bits I observe is 1 0. Right? So this is what we can see from here. For 45 degree, we do get if I suppose this being the I channel, this being the Q channel, I and Q. Let's make it again. 45 degree will be somewhere here, somewhere here. If I consider my carrier wave to be sine, this is where I can draw plus sine. This is where I could draw minus sine. Right? This is where this will be my plus cos, this will be my minus cos. Right? So what are my I and Q here? This is called as constellation diagram. 1 and 1. For this 0 1. For this 0 0. And for this I'm going to write it as 1 and 0. So this shows my constellation diagram. Here every die bit is separated from every other die bit with a phase angle variation of 90 degree. Right? So this is called as constellation diagram. And when I show it with the help of arrow, I may call it phasor diagram. Right? So I hope it is easier for us to draw the constellation diagram as well as the phase diagram. Now let's see how according to this my QPSK waveform can be drawn. What does it mean? Whenever I get to see the die bits 1 1, there will be a phase shift of 45 degree from the original carrier wave phase, right? And if I observe die bit 0 1, I'll observe a phase shift of plus 135 degree, right? I can call this as minus 45 and I can call this as minus 135, right? Right? This is 45, this is 135, this is minus 45, this is minus 45 and this is minus 135, right? So let's see how may I draw the waveform. So for students to learn it quickly and in an easier way, let me draw this waveform. My plus 45 degree comes here, my plus 135 degree comes here, my plus 225 or minus 135 comes here, my 315 or minus 45 comes here. One thing I have to consider is, let's suppose if I observe, if for my ease I consider, let us consider for 0 0. Although I have considered non-inverted as 1, here you can also assume non-inverted as 0. For that case also you'll observe it like for 0 0, if you consider 45 degree. So whenever you're observing dibit 00, you're going to observe a phase shift of 45 degree, right? So the original carrier, which was starting from 0, you'll start it from here and you'll try to make this portion extra which you left here, right? For 0 1, you observe a phase shift of 135 degree. That means your waveform must start from here, and after completing this additional portion will be added up, right? This has been added up. For 225, your waveform must start from here, and when it starts from here, you go up to here, rest of the portion must be added up, right? And for 315, you start it from here and this portion must be added up and leave behind the portion where you have started from. So this is how you can make the waveform for QPSK, right? What are the advantages of QPSK as compared to other modulation schemes that transmit 1 bit per symbol? QPSK is advantageous in terms of bandwidth efficiency. For example, imagine an analog baseband signal in a BPSK. QPSK will transmit double the number of bits as compared to BPSK. So if I talk about the bandwidth requirement for equal amount of bits, my BPSK would require half of the bandwidth of that of my QPSK would require half of the bandwidth which is required by BPSK, right? BPSK uses 2 possible phase shifts instead of 4, and thus it can transmit only 1 bit per symbol. The baseband signal has a certain frequency, and during each symbol period 1 bit can be transmitted. Whereas in case of QPSK, we use a baseband signal of the same frequency, yet it transmits 2 bits during each symbol period. Thus, its bandwidth efficiency is higher by a factor of 2. QPSK is twice efficient as compared to BPSK in case of bandwidth, right? These are the references I have used. Thank you.